Hi everyone, and welcome to the first CS181 video. This one will be on linear regression. So this series overall will just be going over important concepts from the class and trying to walk through the math a little bit more slowly so that everyone can get a better picture for it. So let's begin. The first thing that we'll be talking about is motivation. So that's sort of like why do we want to solve the problem and what is the problem. The second will be intuition, which is at a high level in English, sort of how would we solve this problem. And the third part will be the actual math. So in linear regression, we're going to start with just 2 dimensions because it's a little bit easier to visualize. We'll do more dimensions later. Let's say we have a bunch of people and we know their shoe sizes and their heights. And if we get a new person, we would like to predict their height based on their shoe size. So in a linear regression, what we'll do is for every shoe size, we will predict some height. And the restriction, since it's a linear regression, is that our predicted values have to be linear. So we draw some sort of line, and for every shoe size, we now have some height that we are going to predict. So the big question is, how do we solve this problem? So let's turn to intuition. The first issue we might have is if I draw another line like this, it's obvious this is worse than the initial line. But if I draw another line like this, it's unclear whether the red or the blue line is better. So we need to establish some sort of criteria about how we're going to pick our best line. So the first thing we think is if there's a hyperplane or a line, for context, a hyperplane is just an n-1 dimensional shape in n dimensions that goes through all the points, we should probably pick that, right? So here, if there's some line that goes through all the points, that's probably a good idea to pick that. But in most cases, we're not going to have some exact fit. So our second criteria might be, otherwise we're going to pick the hyperplane that minimizes some sort of distance between our predictions, f of x, and the actual values, y, in the data that we're given. And so our first idea might be, why don't we just take every data point and take our prediction and subtract the actual value, and then add that all up. And that's what our error will be. Well, this is a little too naive, and we can see in this example below, in the first case, we have these 2 data points x, and on our first data point, we're off by +1, and on the second data point, we're off by -1 if we just draw a line straight down the middle. And so under this naive error, then our error is overall 0, which is not exactly what we want. So what we've realized here is that if we have an error of 1 or -1, those are both probably 1, those are both probably equally bad, and 2, there shouldn't be any negative errors that can cancel out positive errors. If you're off, that should just make your error worse. So what we usually do is we use what's called L2 loss. So we take our prediction, we subtract the actual value, and then we square that. And we take the sum of that over all the data points. A natural question to ask is, why don't we just use the absolute value? So the absolute value also has a name, and that's called the L1 loss. And actually, in many applications, you might you can use L1 or L2 loss, and they'll just sort of give you different results, which we'll see later throughout the course. But one advantage of the L2 loss is that it's sometimes a little bit more mathematically tractable, which is nice. And specifically for linear regression, we'll see that minimizing the L2 loss is actually equivalent to sort of a Bayesian framework where you assume Gaussian noise. That's a little bit, we'll do that a little bit later in the course, but just to give some sort of context on why we choose L2 loss. So now let's move on to the math. The first thing is, we've been assuming that we have this sort of prediction function, f of xi, right, where we just stick in an xi and magically we get a prediction. So we need to formalize this with actual math. So let's again go to the 2-dimensional case and we'll go up from there. So we know the equation for a line is mx plus b. So given some shoe size si, we'll take m, the slope, times si, and we'll add the intercept b. And that's going to be our prediction for height, right, because we're restricted to predicting in a line. So now how does this generalize to more dimensions? So let's say we have more things. So now each data point is xi, and the xi contains a 1, which that'll become clear why we need a leading 1. But then it contains more information. So it contains maybe the shoe size, si, maybe it contains some genetic marker, gi, and some other data in there. And before we move on, just a notational note. When I write x sub ij, the first index, I, refers to the data point index. So if we have 10 people, the ith person. And the second index, j, refers to dimension number. So if it's 1, it refers to this leading 1. If it's 2, it refers to SI. If it's 3, it refers to the genetic marker of that person, or whatever sort of covariates we're using. So then if we have this data xi, what is our prediction going to be? Well, our prediction is going to be some intercept b plus m1 times si plus m2 times gi, right? Where we have some intercept, and then we multiply each of the dimensions by some sort of coefficient, because that's the equation for a hyperplane. And again, linear regression, so we have to predict in a hyperplane. We don't have flexibility. With other models, we might be able to predict like cubics or different sorts of shapes, but since we're restricting ourselves to linear, then this is the equation that we're restricted to. So we can actually write this much more conveniently if we write this vector w, and w is just the column vector that's like b, m1, m2, so it's the intercept and then all the slopes corresponding to all the dimensions. And then what we'll see is that our prediction, b plus m1 si plus m2 gi all the way down, can actually just be written as the dot product of w and xi, so just w transpose xi. And now we see why it was such a good idea to put this leading one term here, because for each of the terms in our summation, we have like the slope times the respective dimension, but for our intercept, it just needs to be multiplied by 1 for every single data point. And so in every single data point, we'll just lead with a 1. And this is called the bias trick, because b is also known as the bias term. And now instead of having to carry around like wtxi plus b, we can just write wtxi, and it'll make a little bit of a differentiation and math notationally easier. Great. So now, remember, we're going to be using L2 loss, which is the difference between prediction and actual value squared. So we'll write that out explicitly right here. And now, just like in normal calculus, when you're trying to find critical points, we're going to take the derivative, or in this case, the gradient, which is sort of like a multivariate derivative, and we're going to set it equal to 0, and then we're going to solve for w, right? We want the weights that minimize our loss. So in this first step here, I just use some matrix calculus identities. You can click on the screen here if you want to be linked to a video explaining these in more depth. And then in the next line, I distribute to get this equation here. So we want to isolate w, but it's going to be a little tricky with in this form. The standard form is we write it as matrices. So we're going to convert all of the stuff that we have right now to matrices. And since this is still pretty early in the course, I'm going to walk through how we convert to these matrices, because sometimes it's a little bit confusing, and it's nice to see this sort of process done. So let's talk about the first term here. So sum from I equals 1 to big N of yi xi transpose. So we see every term, we'll just write out the terms of that sum explicitly. So the first term is y1 times x1 transpose, but we'll write out x1 transpose, right, as x10, x12, all the way to x1d is that vector. And then every term in the summand will be similar, except I gets incremented to 2 all the way up to I gets incremented to n. So we see that each of these terms in the summand, each of these terms in the sum is just a 1 by d vector. And so we add those vectors up element-wise, and what we're going to get is in the first term, in the first spot in the vector, we get y1, x10, right, which corresponds to the first element of the first term in the sum. And then every term in the sum is going to contribute 1 part to the first element, all the way through the nth term in the sum, which is going to give us our last term in the first element. And that'll happen similarly for all of the elements of the vector. And so we see that we just get this singular vector right here. And this is actually the product of two matrices. So this is a little bit hard to see, but my strategy for doing this is you don't have to sort of consider every single element of the vector, just consider sort of like the first and the last, or if you're working with a matrix, consider the 4 corners of the matrix and try to figure out what matrices would multiply out to give you just the corner elements of the matrix, or just the first and last elements of the vector. And if you can do that, then probably the other stuff will work out. You should check to make sure, but just when you're trying to think about what two vectors or what two matrices will multiply to this, that's a good way to go about it. So we see that this is actually just y1 through yn. So this is the vector y right here, times the matrix x, right, which is just all of the data points stacked on top of each other. Because we see, so to get the first element, we'll multiply y1 through yn with the first column here. And so we'll get y1 times x1 0 plus y2 times x2 0 all the way through yn times xn 0. And that's exactly what we have as the first element of this vector. And it'll work going through all the columns. So we see that this equivalency right here is true. Great. So our first term in our sum is y transpose x. Now, let's take on the second term in the sum, which is going to be a little trickier, but pretty similar. So we're going to leave the w transpose out in front, and we're going to break down, or we're going to write each of the elements of the sum. So we have x1 transpose, all the way up to xn transpose. And a good way to always check your math when you're doing matrix work is just make sure the dimensions work out, right? x1 is a column vector, it's d by 1. x1t is a row vector, it's 1 by d. And so these two should multiply to a d by d matrix. And then when you add all these d by d matrices up, you should still get a d by d matrix. So again, we're not going to calculate all the things in the matrix. We're just going to calculate the four corners, and then we're going to try and figure it out from there. So we see that in every element of this matrix, there's going to be a sum, and the sum is going to have n parts, right? And each of the n parts of the sum is going to relate to one of the n parts of the original sum. So here, if we look at x1 times x1t, we see that that's going to be d by d matrix. The top left corner is going to be x1 naught squared, right? Because it's going to be the first element in x1 times the first element in x1, because x1t is just a dot product of x1 with itself. And so this actually gives us our first element of the sum. And then similarly, we'll get x2 naught squared. And then when we get down to xn times xnt, that'll just be xn naught times xn naught, so xn naught squared. So that's how we get this element right here. And so similarly, we can look at the top right-hand corner. So that means that's just going to be the sum of the top right-hand corners for all of the elements in this initial sum. So for x1, x1t, we're going to get x1 naught, x1d, right? Because it's the first element times the last element of x1. So again, this comes from there, and then we'll have it all the way out to xn naught times xnd, and that comes from xn times xnt. And so then the bottom left-hand corner is pretty similar, right? Again, but this time it's the last times the first element. Again, there are n terms in the sum because there are n terms in, we're adding together n d by d matrices to get one big one. And then the last term, or the bottom right-hand corner right here is pretty similar to the top left-hand corner. x1t will come out to x1d squared. x2t will come out to x2d squared. All the way to xnt will come out to xnd squared. So now we want to write this as the product of two matrices, and we'll just keep wt by itself again, and we'll see that this giant d by d matrix is actually just the product of x transpose times x. How are we going to see that? Well, let's just check our sort of four corners. So to check the top left corner, that would be the product of the first row of x transpose and the first column of x. And so we see that x1 naught actually just comes from the first element of the first row of x transpose will be x1 naught, and the first element of the first element of the first column of normal x will be x1 naught. So multiplying these together, we get x1 naught squared. Then the second element of the row and the second element of the column will give us x2 naught squared, and this will work all the way down. And we can similarly check the other four corners or all the elements in this matrix, but you'll sort of see by the pattern will work out, and thus this is just x transpose times x. So now we have all of our simplification done, and we can see that from our previous equation up here, from this equation right here, we know that 0 is equal to, substituting in the math we just did, ytx minus wtxtx. And then here we want to solve for w, not w transpose, so we'll just take the transpose of everything. And 0 transpose is just 0, right? It's just going to change. 0 is not a scalar here, it's a vector, but you're just transposing the 0 vector, so you can still get a 0 vector. And then remember that if you take the transpose of the product of two matrices, you just flip them around and you apply the transpose to each of them. So that's just what I'm doing in this line, and then also what I am doing in this line. Great. So now we can solve for w by adding xdxw to both sides and then multiplying by the inverse of xdx. And that gives us our solution. Note here that this part, the xdx inverse times xt, is usually referred to as the Moore-Penrose inverse. But we're not quite done. We should probably check that xdx is invertible, right? Because not all matrices are invertible. So how do we know this? So we want to show xdxu equals 0 if and only if u equals 0, right? And that's the equivalent condition for being invertible. Clearly, if u is equal to 0, then xdxu must be 0, right? Because you're multiplying the 0 vector by something, or you're linearly transforming the 0 vector, so you're getting a 0 vector. And so then we want to show the forward direction. So we know that if xdxu is 0, then u transpose times that will also be 0. So that's how we get our first line to start with. And then remember, applying the transpose trick of product matrices that we did earlier, we can rewrite this first two terms as xu transpose. And this is just the dot product of xu with itself, right? So if the dot product of, or the inner product, of xu with itself is 0, then that means that xu must also be 0. And so we're almost there. We know that xu equals 0, but now we need to show that this implies that u is also 0. We assume that the rank of x is at least d in order to do this. So in other words, the columns are linearly independent. And anytime you make an assumption like this, first you should verify that that modeling assumption makes sense. So why does this make sense? Well, suppose that we have some linear dependence in our dimension. So d1 equals 2d plus 3d3. So in other words, maybe the parts per million of one contaminant is 2 times the parts per million of the second contaminant plus 3 times the parts per million of the third contaminant. And at least empirically in our data that holds. So the data is not, the dimensions are not linearly independent. Well, let's say that the true prediction we wanted to make was like alpha d1 plus beta d2 plus gamma d3 plus b. We could just get rid of the first column of data and instead predict beta plus 2 alpha d2 plus gamma plus 3 alpha times d3, and that would just give us the exact same values. Like these two equations give the exact same thing because of this relationship right here. So if the columns of D were not linearly independent, we could just get rid of them until we had linearly independent columns, and we wouldn't lose any like predictive power. Sort of like saying, in a regression, why would you include somebody's height in centimeters and also their height in inches? That wouldn't make any sense. You wouldn't need to do that. So we can assume that the data is linearly independent. So if we assume the data is linearly independent, you guys might be familiar with the linear algebra fact, xu equals 0 implies that u equals 0 if the columns are linearly independent. But just to explain why that is too, if you imagine the columns, which are the dimensions d1 through dn, we'll say, and then u is some vector u1 through un. If we multiply these together, we essentially get ud1 plus, or u1 d1 plus u2 d2 plus all the way to un dn. And so we know that since d1 through dn, as we said, the columns are linearly independent, the only way to get those to add up to 0 is if the coefficients u1 through un are uniformly 0, which implies that u is 0.